how to choose a basis. They haven't thought enough about how to improve the Ferenczi algorithm. It's just, you know, it's just not out there. It's not part of the culture somehow. Yeah. Yeah.
Oh, I was just saying that's, that's hard to do. How do you choose,
I know.
How do you choose the basis?
Oh, no, but I told you, like, a lot of times you come up with some stupid crude model. What's that? Like, you know, like, well, the speed scaling model, it was easy, because we could come up with an approximate model based on like a fluid model, solve that, and then you got your basis, and it's done. And a lot of control problems are like that. A lot of control problems, you know, you have a lot of structure, you know the value function is convex, you know its growth rate, you know, and then you just take a basis that fits that. And, you know, I was joking the other day, I mean, one of my heroes in this area is Ben Van Roy, who is a student of John Tsoukalos at MIT, and he's now at Stanford. He has this beautiful thesis clarifying TD learning, but then when he actually applied it, he would use like a Fourier series approximation for a function he knew, he must have known was shaped like this. And trying to approximate a function like that with sine waves is not, you know, I mean, it's good to test how well the algorithms work in the worst situations, but I don't think that was what he had in mind. He just, I don't know. For some reason, it's not part of the culture. If you look at that community, there's not much literature or thought about how do you choose a basis. It's just, you know, let's just throw in a bunch of features at random and see what happens, and then tear some away and put some new ones in. That's how it goes. So actually, well, maybe it's a waste of time, but I just want to say, I'll send an announcement to all of you. One of you, thank you so much. Well, two of you, well, actually, at least two of you, actually fulfilled my dream and worked out a policy iteration, a value iteration for the belief state on that Rover problem. And it's so awesome. You know, it's like the structure is basically says, if there's any chance you're on the bottom, you drive. But you're very risk averse about being in the middle. So you know, if there's a moderate chance to be in the middle, you say, "Fuck, I'm not going to drive." And the structure is just fantastic. Anyway, I'll make up solutions as soon as I can with a portrait. And so my conjecture was, you know, the plot needed to be twisted a bit to be correct. So what do we talk about today? So I mean, I think it's most important to explain the variance issues a bit. And because that's the biggest problem you're going to have, is these algorithms don't work unless you understand why they don't work. So let me give you an example. So like Q-learning, I mean, so what we've been doing so far is in these reinforcement learning, we typically have something like this. I'm just going to abstract it for a minute. We have like an expectation of there's some eligibility vector times some function g of some Markov process. I'll put +1 here, and theta. Let's try to get this back in our heads again. So zeta t, for example, would be, well, zeta t is what we call an eligibility vector. I'm not going to write it down again. These are these vectors for Galerkin relaxation. What we really want is the conditional expectation of that given ft to be 0. But we can't achieve that, so we look at this relaxation. And phi t plus 1 is going to be a whole bunch of crap. It's going to be like xt, ut, xt plus 1, and maybe zeta t as well for Q-learning. You know, so the reason I introduced a new variable is because the Markov chain that drives this whole thing can be very, very big. All right? And then we have an algorithm, and you go through it. So that's the thing, is it compactifies things to write it this way. I get an algorithm, which is like theta t plus 1 equals theta t plus, and I wish I'd used n for iterations, but it doesn't matter, alpha t plus 1, and just throw it in. And typically, that's what somebody will use, and you go for it. Now, how would you analyze variance? Here's, let me go through a thought experiment, and you tell me if this works or not. Okay, to save chalk, I'll just write BMM, which sounds rude, but it's this batch means method. I'm revising my stochastic approximation notes to include everything I'm saying right now. So I'll broadcast that to you this afternoon. I'm going to basically run this algorithm for 1,000,000 time steps. And I'm going to do it again and again and again. So 1,000 times I'll run this for 1,000,000 time steps. So let me write it like this. I'm going to do n independent experiments. So, so little n might be 1,000,000, because that's the kind of time you have to wait for these things to work. So a lot of you, when you did the first homework, you were like letting n be 100, or something. It's just slow. I mean, these things are slow. so the time horizon to get a decent estimate by 1,000,000, and maybe do this 1,000 times, and then plot a histogram of what you get. And And this is a vector. So theta t is an RD. This is a histogram of, say, of theta ni. Maybe its first element. Then you look at each element, say of 1. Right? So I run up little n's 1,000,000. So I run this up, stop at a time 1,000,000. I do this capital N times, 1,000 times, and I look at each entry and I look at a histogram, and I see that this is quite narrow, and in fact I know the rate of convergence, so I might scale this or normalize it in some way. Okay, but I find this is really narrow, and I think I kicked ass. I publish a paper, I get the best paper award, and then somebody comes along and has a better algorithm, and they tell you, well, here it is, theta star. So the problem is, I think, did I ever joke about this before? I think I did. If you plotted this algorithm, you would watch the sample paths go like that, and you'd say, my God, I kick ass. It's like perfect. There's no variability. It's converged. Well, you could say the same thing if you just set equal to 0. I can get you the cleanest algorithm by setting alpha equal to 0. You want variability. So the optimal algorithms actually they'll be overshoot. They'll go flying to theta star and then oscillate around it. But you don't know that because you don't know this answer, and so it's really hard. And that's why there's a lot of bogus papers out there. You don't know, and you can get so seduced. First you see this, then you see this histogram with this very small variance, but the true mean is way over here, which you never knew anyway. So what the hell do you do? It's really hard. Yep.
Well, you get that kind of histogram even if you're doing random initial conditions?
Well, yeah, if you knew, well, yeah, that's a good point. So with one of these crappy algorithms, if you actually were more thoughtful, and you put a uniform distribution for the initial theta 0 from here all the way out to there, but you don't know what there is. then your histogram would look totally big. So that's a really good point. So this is going to happen if you chose the initial conditions to be all roughly in the same place. Well, absolutely. But you don't really know how big to make it. But you're right. That's fix number one. Yeah. God, thank you. But we'll see that won't. I mean, that's a really important. Yep. You want to be big then. Yep. You had a point too.
So, I mean, once you arrive at some sort of theta n, can't you plug it back in and just see if you do get like more optimized the cost or something like that?
Absolutely. So fix number 2 is to go back and see if, like, the dynamic programming equations are approximately satisfied. Now, the problem with that is maybe you don't have a model. So the thing that people love about these algorithms is that they're potentially model-free. Q-learning, it's crazy. You can just take data and it spits out a theta star. And if you don't have a model, it could be hard to do that. But most of the times you do have some sort of model. And if it's consistent, if it's pretty good for your model, then you can be pretty happy that you're closer to this and not over here. So that's definitely another thing that one can do. It's just to see if it's consistent for the model you're using. If the DP equations are almost satisfied or whatever. If you don't have a model, that's impossible. All right. And then fix number 3 is to understand what you're doing, understand the source of these problems, and try to make it not happen. So. Understand. And this is surprisingly easy. So it's easier to understand the variance of the algorithm than it is to establish convergence. It's really funny. It turns out that's a simple Taylor series expansion. Well, proving convergence requires some. Well, it requires understanding how you approximate node E, and that's not easy, right? If you want to numerically simulate node E and get a consistent answer, it requires some understanding of numerical analysis, and all this is approximating node E, so it's just as hard as that. And it's a little harder because there's some probability theory that comes in as well. But this is basically, it's not much more complex. Understanding convergence of this is not much more difficult than understanding approximations of node E. I know we've got some step size here. The thing is, of course, there's randomness here, so you have to figure out how to get rid of it in an ODE analysis, and that's, again, where there's some work. But this, I thought we would just try to do it. I'll give you the idea. All right, shall we? Yeah, all right. And then we can think about how to fix it. And so that's today. So how do you do this? So the thing is that we already know how you look at things like that. This is what I called before. Oh, excuse me. I expanded this out just to remind you what an eligibility vector is. But this whole thing is what I called f of theta phi before. Right? And so this is what we're going to do. The first step is to just rewrite this recursion in a certain way. that doesn't look very hard. So F bar was the mean, as I'll remind you. It is so hot in here, I'm going to scream. Isn't it? It feels terrible. Should we open a door or something? Would it help? Thanks, Anon. So all we've done is we've centered things. And this is just for analysis, right? And we're not computing anything like this. But basically, so this is a zero mean process. All I've done is I've added and subtracted this guy. And this is what I mean about no D analysis. Basically, without this, this would be a approximation of an ordinary differential equation. We've introduced this noise term here, and that's where convergence analysis gets kind of tricky. All right, so I can kill that. And also, I'm gonna take that to be 1 over t plus 1. All right. Okay, so you stare at this thing for a bit, and the thing is, this is all faith-based, as I've talked about before. We're going to assume convergence, and then based on that assumption, get a formula for the variance. Okay. Okay, so there's a stationary point for that ODE, f bar of theta star equals 0, and we assume that for any initial condition we converge to that theta star. We'll see that that is true under really general conditions. So under some, of course we need a unique stationary point, and we'll need convergence of the ODE, and stability of the ODE is enough to do it. All right. Okay, step 3 is to linearize. Right, like this. What have I done there? Does that make sense? I've done a Taylor series expansion. Okay, I've said that f bar of theta t is approximately f bar of theta star, which is 0. Plus some linear function of the difference. Okay, so A is the partial derivative of f bar at theta star. Okay, and that is crucial. That is crucial, and you can imagine it's important. I mean, basically, if so many of you are in control, you know that if you want to guarantee some sort of robust stability, you're going to want that linearization near your stationary point to be really stable. So we're going to want the eigenvalues of A to be in the left half plane, out there. So. Okay, so, and we'll come to this. I mean, I can't, there's no time to do these things in class, but when you work this out, like for Watkins Q learning algorithm, this matrix is so awful It's like, it's so tiny, it's practically zero. It's just like its entries are practically non-existent. So remember, keep that in mind, okay? So for Watkins' algorithm, A will have entries which are like really tiny in typical cases. All right, so now what are we going to do with this? I think, didn't I tell you that averaging is a special case of stochastic approximation? I meant to. I did. I said that was the motivation for homework 1. All right, and we know what you do for regular averaging. There's a central limit theorem. You normalize and you expect a Gaussian approximation. So this was faith-based, so you can get away with murder like this. But I mean, after assuming and proving convergence, I can pretend the system is linear. I'm just going to take this for granted. I'm going to replace the nonlinear recursion by the linear recursion as if there's no error. And so, which means I'm adding another error term here, but it's going to be going to 0. So as long as the thing is sufficiently stable, it'll disappear. But the hope now, when you stare at this, is to consider, I'll write this as step 4. Step 4 is just thinking. It's to consider, in the notes I call it ZT equals t times theta, square root of t, times theta tilde t. And the motivation is, again, that's exactly what you would look at if you were just doing straight up Monte Carlo, you know? There's that's what the central limit theorem would be if you were averaging a bunch of random variables. You know, just recall. Oh, let's see. The LLN says this, you know, and if I called that theta t, if you like, and I called that theta star, you know, if I look at the square root of t times theta t tilde, that's going to go in distribution to some n0, I'll call it gamma squared random variable, for nice real valued functions of f, you know. I know I just took a big jump, but now let's take a finite state space Markov chain, say, irreducible finite state space Markov chain, look at sample path averages, then this is the central limit theorem. And averaging is a special case of stochastic approximation. The difference is that we're going to have this A here, A's identity, or minus identity matrix, you know, for that. All right? And consider this. And right there. All right. So this is not an equality. You know, I'll put in light letters an approximation, but I don't want to have to keep writing approximation all the time necessarily. But separately, going to have to do some work to show that even when I multiply by square root of t, I'm not doing any harm by, you know, approximating by linearization. We get away with murder because of this small term in front. So we're introducing something small that's going to 0, then it gets multiplied by this going to 0, and that's how it all works out. So it can be justified. It really can, believe me, trust me. All right, and then what do? This is the crazy thing. It seems so trivial. You multiply both sides of the equation by square root of t plus 1, right? I can erase all this now. I have to. Any questions? The heat, you know, I'm amazed you're also alert.
Why theta tilde is on the left? Like it looks like.
Oh, yeah.
F bar.
So I subtracted a theta star on both sides here. So I get a theta tilde on both sides.
Okay.
And then I plugged in this, this here. And thank you. No, but thank you. That's exactly the kind of thing that you can get. You lose a whole lecture from missing that. Yeah, so I pulled a fast one, subtracted theta star from both sides to get this. All right. But here's where you can really get screwed up because, you know, the square root of t is so damn flat. You know, it's so flat. The square root of t, square root of t plus 1, the difference goes to 0. So if I multiply both sides of this equation by square root of t plus 1, this gets multiplied by the square root of t plus 1. Hell with it. That's practically square root of t. It's exactly the mistake many people have made. It's not true. You've got to do a Taylor series expansion of square root of t plus 1. And the reason is that you've got, this is small too. And you know, it's really tricky. So what you have to do is you have to say square root of t plus 1 is equal to the square root of t. And then you have to remember, you know, your Taylor series expansion, which is 1/2 1 over square root of t. Okay, but plus something which is you know, which is summable. Yeah, I mean it's just nothing. All right. Right, so you just ignore that. We're just you know, we're just approximating, so we'll just stick that in. All right. All right. So if I multiply both sides of this equation by square root of t plus 1, I'm going to be really cautious there, but not so cautious there. I don't have to worry so much because this small term is going to help me out anyway. So there I can get away with murder. I can say square root of t plus 1, square root of t, big deal, because I multiply by a small number. But here, I don't know if this is small. You know, I've got to be more cautious. All right. So I get zt plus 1. That's the left-hand side. Equals. Oh, right there, I'm going to get a zt. Oh, yeah. Oh, thank you. Just checking you. Well, actually, let's see. It's going to pull through. No, it's okay. Now we'll stare at this for a minute when I write this down. So I'm doing this approximation. So I'm going to get. I'll just have to write it down. No, I've got to use my notes. I can't go open loop on this. I don't want to make it longer than it has to be. Yeah. No, I guess it is clear. So I've got this and this is a zt. In my notes, I got rid of the t plus 1. Let's figure this out. So I've got a zt there. Here, if I multiply the top and bottom by square root of t, I'll get a zt over t. I'll do it longhand. Yeah. Forget it. let's do this in our heads. And also, you guys, I forgot an A, right? I had an A there, and you guys let me drop it. All right, but let's stare at this a second. I've got the 1 over t here, which is going to give me a half. And I have an A here, all times zt. Again, you're going to scream, no, 1 over t isn't 1 over t plus 1. That I can get away with. I'm introducing an error of like 1 over t squared. I can get away with that. All right? So I'm gathering together terms. I've got the AZT, and I can't add a number and a matrix, so I have to introduce an identity matrix. And then over here, I will keep the, well, I'll get rid of that as well. 1 over square root of t, maybe. Because it doesn't matter. Some places I know I can get away with murder, and sometimes I can't. But in this case, I'll just keep by my notes. All right. So you had a question? Yep.
Would you mind telling me how you got that zt next to the a? Did you approximate root t plus 1 by root t? You said that was
No, yeah. So I did say so. Yeah. So I cheated here. It was when I multiplied both sides by square root of t plus 1. I had a square root of t plus 1, not square root of t, as you say.
You did have a square root.
Yeah. But the thing is that I'm multiplying by a small number. And that's why I can get away with it. You know, you're right that I'm introducing an error of order 1 over square root of t, but then I'm being multiplied by 1 over t plus 1. And if you recall, that's exactly the order of terms I'm claiming I can throw away. Terms that are summable, I just ignore. Yeah.
So that was
yeah.
t times root t.
Yeah. So this was, yeah. I had a square root of t plus 1. I approximated by square root of t. And you can just, there it's okay, but here I don't have that small term in front. And so I got to be much more cautious. You know, if you go through every single detail, all the big O's and little O's, it's a really long proof. But so they're just telling you what you can justify pretty easily, and these are the steps. So now there's 2 things you can do. So this is fun. So what you've got, one way of thinking about this is you can approximate this as not an ODE anymore, but a stochastic differential equation. So how many of you love Ito calculus? All right. All right. So the 4 of you, we can talk later. But because I don't think I can do it here. But you can actually go through, and I'm going to give you guys a proof of the convergence of the algorithm based on ODE methods. And the exact same approach now can go to this. And you can approximate the process by diffusion. So ZT be approximated by diffusion, where this thing becomes dBT, where BT is a Brownian motion. It's wild, you know. It's really quite beautiful. So if you look at Yin and Kushner, you'll see the best. Their book, you'll see the best exposition of that idea. All right, that's one approach. Is you go and you put this in continuous time by a really special way, which I can explain when we talk about convergence next week. But I'm going to make lives easier and assume that delta t is an uncorrelated sequence, and then we don't have to worry about that. Then it's much easier. So let's throw in an assumption. So let's assume that's an uncorrelated sequence. Before I just said it was zero mean. Now I'm saying it's uncorrelated. All right. So the cross, correlation is 0. And stationary. I'm writing this for a long time. It's driven by Markov chain. It's going to look stationary after a while. So I'm just looking at this for a long time anyway. I'm just going to take the approximation for granted. All right. So that luckily holds for Watkins' algorithm. It doesn't hold for TD learning. All right. And all right, so burn that into your brains. A is the linearization. That's a bit of information you need. All right. Why do I assume it's uncorrelated? It's because then I can take the covariance of both sides, and the cross terms will cancel. So it's much, much easier. Okay. You know, if it wasn't an uncorrelated sequence, so this is, I mean, uncorrelated, it's with all the past. It's, you know, that this is, it's like, not IID, but it's uncorrelated with everything in the past. You know, all the ZTs and delta T's and all of that. So this way I can just take the square both sides and take expectations. And you'll get some big monster, right? But it's not that bad. You know, this is just one big matrix times ZT. You know? And maybe I should have written that out. I mean, do you guys mind? So we've got one big matrix times ZT plus something which is uncorrelated. So the cross terms will cancel out, and we just get the covariance of that and the covariance of that. So it is what time is it? Are we going to do it?
Yeah, 8 minutes.
Oh man, I love it. Life is sweet. Oh yeah. Okay, so I've got this horrible monstrosity, which looks pretty bad. But, so yeah, so the covariance of sigma, that's the covariance of sigma delta. The cross terms vanished. You know, I got this because I took this times its transpose. All good? All right, now what I'm going to do is I'm going to get the middle term, and I get cross terms. But when this thing gets multiplied by itself, that's 1 over t squared. That's summable. That's nothing. So ignore it. Anything summable, throw it away. It's just a little disturbance that won't add up to anything. So what you'll get is, and this was always an approximation anyway, what you'll get is sigma t plus 1 over t times a big ugly mess. And I hope it looks familiar to you. Have you ever seen an iteration like that before? Something equals something plus 1 over t plus a function of time that depends on that. It's stochastic approximation. It's a deterministic stochastic approximation. So I will prove to you convergence is stochastic approximation, and a special case of stochastic approximation is deterministic stochastic approximation, where there's no noise. Now there was noise because these were all approximations. So I will have like summable terms here. There was a 1 over t to the 3/2 and a 1 over t squared, whatever, and all sorts of vanishing terms here. We will prove convergence of stochastic approximation, and therefore that goes to 0. So this converges as t goes to infinity, and it converges to the solutions to that being 0. Si se puede in 8 minutes. What? It means that the covariance actually converges. So what do you find? But check it out. Check it out. It's really. Oh, what does that mean? Si se puede. It's yeah. It was from the what's his name again? The Farm Workers Union. Who was his name again? Cesar Chavez. It was his call to action when he organized the farm workers when they were being abused in the 50s. And yeah. So what happens is the covariance of ZT which is what I called sigma t, converges to something we're going to call sigma theta. And sigma theta is a solution to this being 0, which for control people is a Lyapunov equation. You know. But it's, I mean, it's amazing you can do this in half an hour. I just, you know, considering.
Just throw away all the nonlinearities and look at
Yeah, but still, but still, even for the linear system, it's pretty amazing, you know. I mean, but really, I mean, the fact that you can get anywhere with even the linear system, forget the nonlinear approximations, you know. But you see a few things. If you know linear control theory, you know, shit, this matrix has to be stable for this to exist, you know. And that's the thing. I mean, and people like in Borchar's book, he dropped that term. If you look at his formula, he forgot the half. And it's not true. The variance is infinity if you don't have this. And so you need the real part of lambda of A, any eigenvalue, to be strictly less than -1/2 for every eigenvalue. And I get the feeling that people in the reinforcement learning community do not know this, because they complain about Q-learning being slow, but it would take 10 seconds just to compute this formula and see, well, for Q-learning, it's 0.00053. You know, it's so tiny, it's ridiculous. And it's because of the fact that in Q-learning, if you recall, well, we didn't spend much time on it, but we had these basis vectors that were just indicator functions at particular state action pairs. So for each particular, you've got this giant theta vector, and at each instance, you only update one entry. And so it's a really slow, crawling along process. And so this analysis won't hold for it, right? That's what I mean, so it doesn't work. Yeah, I mean, small, close to 0. Not small, very negative, small, they're clustered around 0. And so this fails, with Watkins' algorithm, with this gain sequence, it fails. Now, so of course, what you guys heard last week, and I mentioned already, is you can increase the gain. So a solution is to use a matrix gain, say. You know, so just take this recursion that we started with, whatever it is, multiply both sides by G. And what'll happen is you'll also multiply the noise by G, so you'll end up changing this as well, you know. And so you'll end up getting 0 equals 1/2 plus GA sigma theta. I'll put a G there just to. Okay, so if A was very small and you try to crank up the gain, let's make the eigenvalues, push them way into the left half plane. So we're assuming A is stable, so its eigenvalues in the left half plane. So just taking G scalar, enormous constant, we can make sure that's true. But when you do that, you make this term larger, and so there's a trade-off there. Yeah.
Larger term means there will be more overshoot.
No, it just means that this will get bigger. So if you take G to be enormous, if you scale G linearly, the solution will scale linearly, basically. And so you can't, I could draw you a plot, but yeah.
G's a scalar, right?
No, G's a matrix. Yeah, you can make it a matrix. So choose a matrix gain algorithm. That's one thing that definitely in most cases you'd want to do. And what's the optimal G? Did I mention this once? I think I did. Yeah, you want the whole thing to be -1. So G star. So if you want to minimize this over all G's, I'm out of time, so it's unfortunate I can't explain this now. I'll explain it next lecture. The optimal G you could ever choose is -A inverse. And that's optimal in the strongest possible sense. It's not the traces minimized, but it's you've got sigma G theta is greater than or equal to sigma theta G star. For any gain you get, in terms of matrices, this is, the difference is positive semi-definite. This matrix minus this matrix is positive semi-definite. So you give me any gain, it won't be as good as choosing that. All right? And that can be estimated based on data. You know, basically, I know it looks hard because I said it's a race now. A was the derivative of this weird thing with respect to theta. But for Q-learning and TD learning, it's right there in your face. It's obvious what that is. So you can estimate it.
Really small values, you're really close to seeing that.
Yeah. You're absolutely right. So if A is really ill-conditioned, then this is going to be a problem. You're going to get numerical problems. But we're going to come back to this next time. If A is so badly conditioned, maybe your basis was not very good to begin with. Maybe you should restructure your algorithm back there. Maybe you should, you know. So we'll talk about those design issues next time and we'll go a bit further. Yeah. Because we're out of time, I think. I forgot my watch. Time's up. Yeah. Okay. So yeah. So next time we'll talk about these design issues more, and we'll. I'm still. There's so many things to say. I don't know. I'm still. I'll get, if anybody has feedback for me, like that design issue about how to maybe redesign the basis. There's something called Polyak averaging, where you avoid this whole thing altogether. It's crazy, and sometimes it works. There's so many things we can talk about at this point. I don't even know where to. So I want to talk about a lot of design issues, and I'll wait till next week to prove convergence. So some of you need to know that.